ZombieFinder, one of the SysNocturnals tools, is specifically designed to identify zombie processes and threads on Windows, and very importantly, the processes, the user mode processes, keeping them in an undead state. All right, quick spoiler. Let's just have a look at the tool, see what it outputs, right? It requires admin rights, ZombieFinder. Okay, we've got here a list of user mode processes that are holding zombie process and thread objects. So you've got the process name, the process ID, the number of objects it's holding in kernel memory. You've also got, for no process, this is kernel references that are keeping these undead objects in an undead state. ZombieFinder comes with a bunch of command line options, and the one I tend to use the most to get lots of details and to output as tab delimited CSV. Pipe that to the Windows clip utility, which takes that text and puts it straight onto the clipboard, which makes it really easy to paste into Excel, where you can now do all kinds of filtering and sorting, et cetera, et cetera, et cetera. That's the spoiler. Now, what the heck am I talking about? What is a zombie? Well, a zombie is a specific type of resource leak, specifically a process or thread object in kernel memory, a representation of a process or thread that exists in kernel memory long after the process has exited. Ordinarily, they're gone after the process or thread has exited. When these accumulate in large numbers, this can be a serious performance killer. The thing is, they can be reliably detectable, but not using any of the standard tools that come with Windows, or for that matter, the SysInternals tools. So what causes zombies? The number one cause is a long-running process. You've got a long-running process that acquires a handle to another process or a thread in another process, never closes that handle, and then the other process exits. That's the number one cause. It can also come from kernel code references. Some kernel code, maybe an antivirus or an anti-cheat driver on a gaming system, increments the reference count on a process or thread object and then fails to decrement that counter. In the case of kernel mode references like this, it can be difficult to impossible to reliably identify the guilty party. Let's dig in a little bit more. What are handles? Well, handles are the mechanism through which user mode processes access resources managed by the kernel, such as files, registry keys, processes, threads, synchronization objects, etc. Here we have sampleapp.exe, okay, running in user mode. It has a corresponding process object in kernel mode that has a handle table with references to the resources that it can access. So sample app wants to open a file. So it calls an API. In this case, it's actually a pseudo API, but just for demonstration purposes, it calls an API that interfaces with the IO manager in kernel mode. The IO manager allocates memory for and creates a file object, which is used to access the corresponding bits on disk. A pointer to this file object is added to sample app's handle table, which increments the file object's handle count. The user mode process gets the handle value, which is actually the index into its handle table, and that references the file object. Here it assigns it to a variable called h. So h has the value 4, which when referenced in the handle table has a pointer in kernel memory to the file object in kernel memory. So when sampleapp.exe wants to access the file, reading the file in this example, it passes that handle value 4 to the corresponding API. The IO manager performs the requested work using the referenced file object, in this case returning the requested data. This part's important. When sample app is done using the resource, it needs to release or close the handle it received. These objects are reference counted. When the last reference to an object is released, it is deallocated, and the memory it had been consuming is available for other use. So what happens if the process doesn't close those handles? Well, kernel objects just accumulate and consume system resources. And note that process objects are the most resource intensive of all the object types. Now, when a process exits, like sample-app.exe exits, all the handles in its handle table are closed, and objects with no remaining references to them are freed. But when you have a long-running process, that might never happen. One frequent cause of zombie processes is incorrect use of the Win32 API used to start new processes on Windows. So when the create process API succeeds, it returns two handles to the caller through a process information structure, one handle to the new process and one to its initial thread. These are now in the calling process's handle table, and it's the calling process's responsibility to close those handles when they're no longer needed. So what can it use it for? The caller could use the process handle to wait for the process to exit, as shown here. But in any case, it must at some point close both of those handles. And this is something that sometimes devs fail to do. And by the way, even if the process handle is closed but the thread handle isn't, the corresponding thread object will remain in kernel memory, which will also keep the corresponding process object from being freed. What is the impact of zombies? So here, the system starts out with these portions of kernel memory taking up very little RAM, plenty of system commit, plenty of physical memory available. A long-running process, in this case a demo program called ZombieMaker, starts a whole bunch of short-lived processes. The green ones are the newly started processes. The red ones have already exited. But ZombieMaker doesn't close the returned handles. So now at this point, all the child processes are gone. They've all exited. The ZombieMaker process takes up very little memory in user mode, but it has a bunch of process handles that it hasn't released. So what happens to system resources? Boom. Kernel memory taking up lots more RAM, including non-paged pool, which must remain resident in physical RAM. System commit nearly exhausted. The system becomes nearly or increasingly unresponsive. So why are zombies invisible to standard tools? Because of limited support in the Win32 API set for identifying processes that have exited. The process enumeration APIs at the Win32 level don't list or report processes that have exited. You won't see them in Task Manager or any other standard process listing tool. And many of the process query APIs don't work for processes that have exited. For example, here, Process Explorer, SysNocturnals Process Explorer, using Win32 APIs, it has the process ID of processes for the handles it's got, but the APIs that it can call from the Win32 level won't give it the name of the process that it had when it was running. So I said earlier that zombie process leaks are reliably detectable where other leak types aren't. So let's clarify what constitutes a leak. Basically, a process has had a resource allocated but has lost track of it. So it can't use the resource, and it never frees the resource because it's incapable of doing so. It doesn't have the reference to that object anymore. It's just lost it. But when you see a process that's increasing its consumption of resources, can you tell whether it's actually a leak? So for example, we can see when a process's memory use continually increases. Is it leaking? Maybe, maybe not. Run SysInternal's process monitor for a while, and you'll see it consuming more and more memory. But it has to because it's gathering more and more data about all the events it's monitoring. So it's not really lost track of it, but it is increasing. So the thing about resources like memory, files, etc., is that as long as you've got them, as long as you have access to them, they're still usable. So in most cases, it's not feasible to determine reliably whether a process is losing track of its resources without actual source code access. But when a process or thread has exited, it can't be used anymore. It can't be brought back to life. You can get its exit code, but that's just about it. So when a process is holding handles to lots of these things, you can be pretty sure it's a leak. So Bruce Dawson came up with a really clever way to identify the existence of zombies and the processes that are holding on to them, that are have these outstanding references to these processes and threads that have exited. And what he does is he uses an undocumented API to enumerate all the processes. This is a native API exported from NTDLL. And it identifies, it goes through all those processes and identifies the ones that have exited. It also, for those processes, the ones that have exited, enumerates any remaining thread objects in those zombie processes. It then gets, using another undocumented API, it gets all the handles in all the user mode processes handle tables. That's a really clever thing to do. And then matches up those handles to the zombie processes and threads. So find zombie handles written in C# and also open sourced. So ZombieFinder was directly influenced and inspired by Find Zombie Handles, but it makes a few improvements. Number one, it's written in C++ with no DLL dependencies outside of what's in Windows already, no .NET dependency. It's faster, it's more efficient, it releases resources more quickly. Importantly, also, it doesn't consider a process to be a zombie if it had just exited. By default, it waits 3 seconds before determining that a user mode process may have lost track of a handle, because it's not unusual for a process to exit and then something waiting for it to exit to get its exit code or something like that. So we give it a little bit of time before determining that this is a zombie. It lists zombies that are being caused by kernel references. If the responsible process, user mode process, hosts one or more services, it lists those. It also provides the option for tab delimited output, which, as I showed, works really, really well with Excel. The summary view is very concise. The details option gives lots more detail than Find Zombie Handles does. So a bit more demo. First, let's go back to the Excel that I've got here. So what we've got the owning process name. This is the process responsible for the leaked handle, the process ID, the full path to that process, the value of the handle. Oh, any services. If there's any services, they'll be listed as well. So like we've got here, let me just here, we've got a couple service host instances, one hosting user manager, the other hosting PCA service. Okay, the handle value in the handle table, the process ID. If there's a thread ID, that's because there's a thread handle being held. The zombie image path. This is the process that exited, when it started, when it exited, how long ago, and the parent process that started it. So here we've got searchindexer.exe, launched search protocol host.exe, Outlook acquired a handle to it and failed to release it. Here's another interesting one. This is a bug in Explorer. Every time you're at the console desktop and you lock and unlock the workstation, an instance of Logon UI that had been started by WinLogon, Explorer has acquired a handle to it and it leaks it. Oops. In those numbers, though, small handfuls of zombies like this, that's not a big deal at all. It's only when they accumulate in large numbers that becomes a problem. So to demonstrate that, in the SysNocturnals tool set, there's also something called Zombie Maker. And this is just a demo tool that creates a bunch of child processes. You saw the screenshot of it earlier. Creates a bunch of zombie processes, leaks the handles, and then waits until you press a key to exit. So as long as it's still running, you've got tons of zombies. So let's do 500 of those. Let me first do ZombieFinder And you see no zombie maker here. Zombie maker. Okay, it's now leaked 1,000 handles, 500 processes, 500 threads, and it's waiting to press any key. And if I do zombie maker now, or I'm sorry, ZombieFinder, there it is, 1,000 objects leaked because this thing has failed to release them. Another thing, though, is if we decide, like, hey, let's give it a little bit more time, anything under 30 seconds we'll call a false positive. It filters that out. So only processes that exited more than 30 seconds ago are considered zombies. By default, the value is 3. You can also do 0 if you want, and then any process that's exited is going to be listed in there. And here no false positives this time. Okay, release those handles. And zombie maker is no longer in the list. Okay, let's have a quick look at some zombie-specific symptoms and things that aren't symptoms of zombie processes. So you've probably seen this. This is not a zombie. This is a hung process. It's a GUI app that isn't responding to window messages such as notifications about keyboard or mouse events. Here's another non-zombie. This is an example of an unkillable process. Not because of failed access check, as the error message suggests, but because there's an IO request that's not returned from the kernel, neither completing nor canceling. This is sometimes called a zombie, but it's a different kind because the process hasn't actually exited. This isn't the kind of zombie ZombieFinder is interested in. Here we've got a process consuming a lot of memory. This might be a memory leak, but that's not evidence of a zombie process leak. Remember that zombie processes manifest in leakage of kernel memory, not a process's memory. High handle count can be a symptom of zombie leakage. After all, it's one of the ways that zombies can come into being. It's not a definitive symptom, though, because those handles could be to other object types, and it could even be lots of duplicated handles pointing to a single kernel object. By the way, this handles column in Task Manager, you can get that in Task Manager. Just right-click on the column headers in the Details tab, select columns, and then you've got a bunch of other columns you can add, including handles. So that's how you can get that. Okay, very large process ID numbers are usually a pretty solid indication that there are a lot of process and or thread objects that aren't getting cleaned up. Those objects IDs can't be reused until the objects have been cleaned up, so you end up with really big numbers. Process and thread IDs come from a common pool, and the process ID cannot be reused while there's already a process object in kernel that has that ID. So when a lot of them exist, you end up with really, really big numbers like this. So this is a reliable symptom. And that's it. And I will post the links to these references in the someplace. You'll find them. This book, I highly, highly recommend this book. It really helps with everything you ever want to do, and it makes a great gift. Oh, and by the way, this is the Excel macro that I used when I was quickly converting all that tab delimited stuff in Excel into sorting, filtering, et cetera, et cetera, et cetera. Okay, that's it. Thank you very much for your time. I hope you find it useful.